Okay, so today we're going to continue to look at vortices, right? Essentially what we're going to do today is to look at both how flow fields behave around vortices and how vortices behave in a flow field. And this is going to lead us to our next topic, that's incompressible potential flow. So basically we are going to explain how a flow field looks like around the concentrated vortices, and then we'll dive into not only the kinematics but also the dynamics of flow fields, particularly flow fields in regions that are a little bit far away from vortices, right? These are the potential flows. All right. Okay, so this is really the last lecture on the fundamentals before we dive into the incompressible potential flows. And there is also a schedule on the lab sections, and we just did the wind tunnel 2 last Friday, and this Friday we are going to do aerodynamic analysis using AVL. So that's a software that you can use to analyze the induced drag, the dynamics of airplanes. And then we'll look into X-foil, essentially looking at airfoil sections. And we'll have 2 Wright brothers wind tunnel sessions, and then we'll look primarily into computational fluid dynamics. All of this is going to be helpful in the project you'll be doing. All right, so how does airflow around the vortices? Right, so in the last lecture, we looked at what is the definition of vorticity, the curl of velocity, right? In particular, we know that the vorticity has 0 divergence. That means vorticity, a vortex cannot really end anywhere. And in this lecture, we'll look into more consequences of the fact that vorticity cannot end, right? We'll look at what is the consequence on the dynamics of vortices. In particular, how does a vortex change its orientation in a non-uniform flow field? But first of all, we are going to focus on how air flows around the vortices, right? So again, we'll use this seemingly complicated relationship that describes what is the velocity field around a single vortex. And basically, this is assuming incompressible. So basically, also this is assuming the divergence of velocity is equal to 0, right? In this context, how is the velocity field behaving around a vortex? So to understand this relationship a little bit more, let's not just look at the equation like as a dead equation. Let's actually look at an example where we have a segment of vortex. So let's imagine we have a vortex that is going from one place to another place, a straight section of vortex, right? We know a vortex cannot end, so we know the vortex cannot really begin at this point or end at this point, right? But the field induced by vortices are additive in the sense that if the vortex continues to infinity or even turns, we can add up the contribution from the different segments, right? So let's just focus on one particular segment, and let's approximate this segment as a straight vortex. And then let's look at one particular point that's away from the vortex and use this equation to figure out what is the velocity induced just by this segment of vortex, right? So we'll perform the integral, right? We are going to integrate over dl. So dl is going to be this particular small section, right? This is dl. And what is r? R is the distance, is the vector that points into the flow, into the location of the flow field from this small segment. Right, this is R. All right, so if we write the whole thing into a coordinate system, so let's actually denote x as the direction of the vortex, and y being orthogonal to x, but in the plane of that point, in the plane of both the vortex segment and the point we are computing the velocity on, right? So then, we actually, let's take this, the beginning of the vortex as x equal to 0, and x equal to L is the length of the vortex. And so the distance between the vortex and the point, let's denote it as d, as the distance, right? Then we know that r is simply equal to the square root of d squared plus, like the magnitude of r, right, is equal to square root of d squared plus x squared, right? And the dl as a vector is just equal to dx and 0, right? And r as a vector is going to be equal to the x component of r is going to be really okay. So the x component of r is going to be the location of the dl of the segment x. So let's say dl is at x minus the location of the point. So that's x naught. And the y component is going to be d, right? Okay, now when we look at plugging these quantities into the Biot-Savart law, we need to first evaluate what is dl cross with r, right? Question?
In the magnitude of r, don't you mean x minus x naught?
In which one?
Magnitude of r.
Oh yeah, in the magnitude of r. Yeah, that's right. Sorry. Let's also revise that with let's see, x minus x naught squared. Yeah. Okay. Now, first of all, let's compute what is the numerator. So what is dl? What is dl cross with r? Okay, so first of all, we see that dl is completely aligned with the x direction, right? So the x component of r actually does not matter at all. The only contribution from this cross product is going to exist in the z component. So basically, because both vectors are in the xy plane, right? So the x and both vector has 0 z component. That means the x and y component of both of the cross product are going to be 0, right? Okay, and the z component doesn't depend on x minus x naught. It only depends on dx and d. So the cross product is going to evaluate to dl goes into that direction, r goes into that direction, so it'll come out of the board, right? So it's positive z. So we have dx times d. All right, agreed? Okay, so here we can immediately see that the numerator does not depend on the location of the small segment we are integrating over. But the denominator goes like r cubed, right? So essentially, the amount of contribution from a small segment goes not just the inversely proportional to distance, but inversely proportional to the distance cubed, right? Okay, so let's actually do that calculation over here. So the integral over, so instead of going from minus infinity to infinity, so we are going to be integrating with x goes from 0, right, to a length of L. And we have gamma over 4 pi that comes out. So we don't carried in the integral. So dl cross r is just a d times dx, right? And the numerator is x r magnitude to the third power, which we already have the r magnitude over here, so it's d squared plus x minus x naught squared to the 3/2 power, right? So that's gonna be my integral. So that is my velocity is equal to that. All right, any questions so far? Yeah?
I'm still confused about why did you write the divergence of that velocity here? Is that not assuming that the flow is incompressible?
Yes, very good question. So this law actually works only when the divergence of velocity is equal to 0, right? In general, if the divergence of velocity is not equal to 0, you have to complement. In order to calculate the flow field, you need to both know the curl of velocity, which is vorticity, and the divergence of vorticity, right? These two pieces of information uniquely determines a three-dimensional flow field. So although the vorticity has 3 components, but we know that vorticity by definition has 0 divergence, right? So the 0 divergence criterion actually removes 1 degree of freedom from the 3-dimensional vector field. So essentially, the amount of information contained in the vorticity field is actually only equivalent to a 2-dimensional, like 2 components. So it's not like 3 independent components of information. So you need 1 additional scalar field to uniquely determine the vector field V, right? And that additional scalar field is actually the divergence of velocity. So basically, in the scenario where divergence of velocity is equal to 0, that's the scenario you can completely determine the velocity from the vorticity field, right? And this is the simple equation that, I mean, not so simple, but like this is the closed form of how the velocity actually would depend on the vorticity field, right? In general, it's actually so if you have a 3-dimensional vorticity field as opposed to concentrated vortices, you are really integrating in 3 dimensions instead of integrating in 1 dimension. But the equation simplifies to a 1-dimensional integral when you have concentrated vortex filaments. Yeah, good question though. And why is it relevant? This is because usually away from airplanes, right? So if you look very close to airplanes, if it travels significantly faster compared to the speed of sound, you get compressible flow. But when you look at, for example, the wake of airplanes or locations that are sufficiently far from airplanes, the velocity field compared to the speed of the airplane is relatively low. So even if the airplane is traveling at a finite Mach number, the velocity field behind the airplane or sufficiently far away from the solid geometry can usually be approximated pretty well with a incompressible flow, right? When the Mach number is much less than 1. So this equation actually works quite well in describing the flow field behind the airplanes, even if the airplane travels close to Mach 1. All right, so that's why this is relevant even for compressible flows. All right, okay. So now, basically, we are focusing on the velocity induced by a finite segment of a straight vortex, right? And this can be written in such a way. And to perform this integral, whenever actually you see the addition of a constant squared plus another square that involves the variable that you need to integrate, a good way of performing the integral is to change the variable. So instead of having x over here, you change the variable so that x minus x naught is equal to d, which is the constant over here, times a tangent of a certain theta, right? So that actually has a physical meaning here. So x minus x naught is basically this distance, right? This is x minus x naught. And d is the vertical line. So the tangent theta, the theta here is essentially this angle we have in this diagram. Okay, so instead of now integrating over x, we can integrate over theta, right? So we can draw, we can say, okay, this is this angle, this negative angle here is theta naught, and this positive angle here is theta L, right? So that'll be the beginning and end of the integral. So this integral now becomes the gamma over 4 pi is still outside. The ends of the integral would go from theta naught. In this diagram, it's going to be a negative value to theta L. Okay, and the d times dx, because dx is dx minus x naught, right? So we get a d squared in the numerator, and a d of tangent theta is what? You can usually use a diagram to figure out what is d of tangent theta, right? So if theta increases by a little bit, the d tangent theta is basically the increment in x, right? And you can draw some triangles to figure out this is d theta times cosine theta to the negative 2th power, right? So basically you need 2 division by cosine thetas to get this segment. One to get the length of this green line, and the other go from the d theta, which is the radius over here, to the x direction distance. Okay, and then what's really useful is the denominator. So let's pull out the d cubed over here. So basically the d squared to additional 3 over 2 power becomes d cubed, right? And inside it, you're going to see like we have another d. D is going to be squared, so that also contributes to the d cubed. But then we have 1 plus tangent theta squared, right? So that goes into our Pythagoras theorem, and we are going to get, basically this is going to be 1 plus tangent squared theta. So what is 1 plus tangent squared theta? It's 1 over cosine theta squared, right? Okay, so that's going to cancel with the cosine theta to the minus 2th power, right? We get a minus 3 power over here, and that gives me 1 additional cosine theta. So gamma over 4 pi integral, the same ends I'm going to skip over. So 1 over d, right, that cancels out. And we get a cosine theta d theta. So everything becomes a lot simpler. Any questions in this simplification? So there is a cancellation of d squared with d cubed. There is another cancellation of cosine theta squared with cosine theta cubed. All right. Okay. So this actually is easy. What is integral of cosine theta, right? It's sine theta. So basically we get outside gamma over 4 pi d. The difference between sine theta, sine of theta L, which is the upper bound of the integral, minus sine theta naught, the lower bound of the integral. Okay, so that equation, let's interpret the physical meaning of it a little bit. So first of all, it's actually relatively easy to think about an infinitely long vortex. So an infinitely long vortex corresponds to theta naught of what? Minus 90 degrees, right? And theta L of plus 90 degrees. All right, do you have questions on like the derivation?
No, I'm good.
Okay, yes? In the numerator, right? Okay, sure. So in the numerator, the cosine comes out this way. If you have a tangent, right? So if you have a tangent theta, and you are looking at d tangent theta. Sorry, it's very hard to draw without the pen over here. So basically, theta increases by a little bit, right? What you are looking at is so this is tangent theta. So this is tangent theta, right? And therefore, this increment over here is the d tangent theta, right? So d tangent theta is this small segment, while the small difference in the angle is d theta. That's what you're asking, right? Okay, so, and this, where this is 1, right? If this is 1, this is tangent theta, and this is d tangent theta. Okay, so this line is 1 over cosine theta. Agreed? Right, because the ratio of the 1 to this line is cosine theta, right? So this is 1 over cosine theta. Okay, and therefore, if you draw a line perpendicular to the hypotenuse over here, that small perpendicular line is equal to 1 over cosine theta times d theta, right? Okay, but this is not the vertical segment. So basically the perpendicular line and the vertical segment forms a similar triangle to this triangle over here, right? So to get this small vertical segment, you need to divide this d theta over cosine theta by another cosine theta, right? So that gets you d theta over cosine theta squared. All right, this is usually like it's very hard to remember all these calculus relationships with trigonometrics, but like derivation, I found it actually much easier to remember than remember like all the formulas. All right, does that answer your question? Okay, any other questions? Okay, so let's first interpret the conclusion we get, right? For an infinitely long vortex, which corresponds to theta L equal to minus pi over 2 and theta naught equal to pi over 2. So the sign of minus pi over 2 is minus 1, right? Sign of pi over 2 is plus 1. So we get, sorry, this is minus 1, this is plus 1. So we get 2 in the parentheses, right? That cancels out to be gamma over 2 pi d, right? That's exactly, I'm pretty sure what you learned in unified on the velocity induced by infinitely long vortex. And another thing you learned in unified is the velocity field induced by a semi-infinitely long vortex, right? That's used in calculating the induced flow on a finite wing, right? So basically, the trailing vortex goes behind the airplane to infinity. So what that corresponds to is a theta L, again, equal to pi over 2, but theta naught equal to 0, right? So basically, theta naught equal to 0 means the vortex starts over here, okay? So that, for that scenario, this parenthesis evaluates to 1, right? So that's gamma over 4 pi d, okay? And the velocity goes inversely proportional to d. That's always the case. But this really generalizes what we learned before in the sense that you can numerically now compute the velocity field induced by a vortex of any shape by approximating that vortex with small straight segments, right? And they use this to evaluate the contribution from the small segments one by one and adding them up. So with this, you can start to calculate, for example, the downwash on a swept wing, right? Or the downwash on a wing with winglets, right? So things like that you can start to do with this formula. Okay, any other questions? Okay, so now we looked at the airflow around vortices. How do vortices flow in air, right? So that's kind of two things. If we understand both, we can basically understand the vortex-dominated flow fields. So what we have learned in unified is basically in the uniform flow field, the vortices just goes straight, right, behind the wing, assuming the flow field behind the wing is actually free stream, right? There is no induced flow. Then we can calculate that the vortices just goes straight back. But there is a contradiction here, right? There is induced flow by the vortices. So the flow field behind the wing is not going to be uniform. And we did not learn how vortices behave in a non-uniform flow field. So here is the important equation here. Again, this is assuming, this equation is assuming that the velocity induced by vortices, assuming the divergence is equal to 0, and the equation over here that governs the evolution of vorticity is assuming rho is equal to constant. Okay, we'll defer the analysis of a rho not equal to constant case to a compressible flow section. So the equation becomes a little bit more complicated, but not that much more complicated for compressible flows. Okay, what you see here is that there is a source term. There is a term that is like the diffusion of vorticity. So this operator, the gradient, this is not the gradient of gradient, this is the divergence of gradient, right? Also known as the Laplacian operator. So what the only thing you need to know about this operator is that this is exactly the same differential operator that governs the heat equation, the diffusion of heat. Okay, so from that you can very intuitively understand what the term is doing. So this is kinematic viscosity of air, which is very small. And this is, so it is equivalent to the conductance, like this is equivalent to the ratio of conductivity of heat to the heat capacitance, okay, in a heat equation. So if mu is very small, the heat is basically equivalent to almost like a heat insulator, right? Something that has very poor conductance, or something that has a combination of poor conductance and high heat capacitance. So what that means is that if you have high temperature in one place, low temperature in another place, it is going to diffuse slowly, but very, very slowly. So that's the same thing for vorticity in air, right? A very concentrated vortex filament is going to diffuse to a slightly wider vortex filament, but it takes a long time to do so. So in viscid flow, we basically ignore this term because of this term works so slowly, right? So we'll only focus on this term. And the only thing important on this term we'll emphasize right now is that if there is no vorticity to start with, there is going to be zero vorticity you're going to end up with. And what this term actually does, I'll just say it without any derivations. We'll leave the derivations later when we look at dynamics. So what this term does is primarily changing the strength and orientation of existing vortices. Okay, right? So the change of the strength of the vortex is usually called the vortex stretching. Okay, so it's almost like you take a vortex, you stretch it, and the vortex becomes stronger. Okay, by stretching it, it's like stretching by different velocity in the beginning and end of the vortex. Yes?
So from there you're saying that if you have incompressible flow, there's no way you can generate a vortex.
If you have incompressible flow, there is no way you can generate a vortex?
Yeah.
So yes, that's true, except for on the solid boundaries. The velocity on the solid boundary has to be zero, right? So if you have a non-zero velocity right next to the boundary, then there is vorticity by definition, right? From the definition of vorticity here, right? So even if you have zero thickness boundary layer, then you have infinitely strong shear, like you have infinitely strong vorticity over here in the boundary. And that's going to drive this diffusion term that forms the boundary layer. Yes, but otherwise there is no way you can generate vorticity. Yeah, in the incompressible flow field with conservative body force, right? If you have non-conservative body force, somehow you can generate vortices by using like a rotational body force, right? Yeah, good question. Yeah, vorticity cannot really be generated away from the boundaries. Okay, so now what's important about this conclusion is that if you look at a wing, right, and a wingtip vortex, so we know that what is the flow field. So let's ignore the trading vortices for now, right? We know there are going to be bounded vortices inside of the wing, right? So that's kind of going back to unified fluids, right? We know that a wing, when producing lift, has circulation around it, right? And the circulation around it can be thought of as a vortex that lives inside of this wing. It's not a vorticity in the fluid, but it's almost like imaginary vortices inside of the wing. So there is going to be a vortex that looks like this inside of the wing. What is the flow field induced by this bound vortex segment? Right? We use exactly what we learned in the last slide, right? We have a vortex like this. The flow field is going to rotate around the wing like that. And in particular, right behind the wing, the velocity goes down, right? Okay, now if the velocity goes down, we have the evolution of the trading vortices, then it also has to go down, at least initially. Right? Why? Because the vorticity goes with the flow field. This is material derivative, right? This derivative is basically the derivative of vorticity as a flow particle travels with the flow field. So if, for example, you're asking, is there a vorticity at this point? I only need to look at what is the history of the fluid particle before it reaches this point. If there is vorticity in its history, then there may be vorticity at this point right now. If you trace downstream, the point misses the solid body of the wing, right? Then there is no way that location has non-zero velocity, vorticity, right? Just because of this equation. That's the most important consequence of the vorticity equation over here. So a place can only have vorticity if you trace upstream through the history of that fluid particle. And there is vorticity generated in its history. And in this scenario, the only reason is that the streamline, when you trace upstream, would touch the surface of the wing. Right? Okay, so that means if the flow field, the downstream of the wing, is going down, what does that mean for the vorticity field? The vorticity, so there is only, so imagine the flow going over the wing, and imagine a imaginary sheet that is aligned with the flow field, that originates from the surface, right? And is aligned with the flow field. The only location that can possibly have non-zero vorticity is on that sheet, right? That intersects with the wing. All right, so, and that sheet of vortices, of potential non-zero vortices, would go down initially, would go down because of the induced flow field, right? Imagine this is as an imaginary sheet. This goes down initially, and the downward motion would become less as you move further and further away from the bound vortex inside of the wing. So this is going to go curve like that, right? Which means that if I have only concentrated tip vortex that comes out of the tips, that tip vortex is going to go down and then go straight. Right? So that's the first consequence that's different from like the simple approximation we learned in unified. Okay? And then now, if you think about this curved vortex, we know like a straight vortex does not induce any velocity on itself, but a curved vortex does. Right? Right? A curved vortex, if you think about the effect of this segment to this segment, d is not 0, right? What is the effect of this segment on this segment? Is it going to, so basically a downstream segment that is below the wing, right? What is the effect of a downstream segment below the wing on the velocity field of the segment of vortex, of the velocity right downstream of the wing? Is it upward, downward, inward, or outward? Yeah, again, like let's draw the direction of the vortex field. The direction is like this. So what is the effect of this segment on this location? So let's say this is dl, and this is my location. Use your right hand. Yes, span-wise, that's correct, right? Which direction span-wise? Because like the delta distance, right? R lies in which direction? R lies in so let me draw coordinates. So this x is the downstream coordinate, z is upward coordinate, and y is the span-wise coordinate, right? Then R is going to be lying in the xz plane, right? And dl is aligned in the x-axis, right? A cross product between x-axis and something in the xz plane has to be in the y direction. So yeah, it induces a span-wise flow, but in which direction? Yeah, inboard, right? Yeah. Inboard. Similar, this vortex over here again introduces an inboard flow over here, right? So the velocity field induced is going in like that. Yes? Question?
When we're talking about induced fields, that the speed at which they induce or whatever force is induced should be like less than the speed of sound, right? Or the speed of sound.
Oh, it's so in this case we are talking about the flow field that are much less than the speed of sound, right? For all these relations to be true, right? The divergent velocity is equal to 0, rho is constant, right?
So you're basically just assuming that everything is going to be induced.
Yes, right. The airplane may be traveling at Mach 8 or whatever, right? But the flow field relative to the ground of what's happening, like several chord lengths downstream of the airplane, is going to be having a low Mach number. Yeah. So yeah, that's right. Yeah. Okay. Yes.
I'm confused about what I'm looking at here. Is this like a cross section of the wing, or like where
I'm trying to do a three-dimensional drawing over here. Sorry for the confusion. So again, the span-wise direction is y, and the airplane is traveling in the minus x direction. So after like away from the airplane, the vortices would be basically going in the x direction, and the z direction points up, right? Is the direction of lift. Is it clear, like the three-dimensional drawing we are trying to draw over here? Yeah, sorry, I should have explained in the beginning. Yeah, question? Other questions? Yeah.
So we're doing dl cross r.
Yes.
And r is in the z direction, is that
r is in the x and the z direction, right? So r is this position minus the position of this vortex that's inducing the flow field.
R is okay.
R is this minus this, right?
Yeah. So that's in this. That's in the same direction as dr.
That's not in the same direction as dr. If this vortex curves, right? If this vortex is straight, then r is in the same direction as dr. Then the cross product would become 0,
Yes.
right?
Okay.
So,
Yeah,
but
I
if this goes down first and then goes in the x direction, then the cross product is not 0. Yeah. Okay, so think about this, right? So if the induced velocity from the bounded vortex goes down, and the induced velocity from the trailing vortices goes inbound, right? Then what is the direction of the tip vortices when it first emanates from the tip of the wing? I mean, if this is the direction of the travel, it is going to go down. It's going to go down and go inward, right? Before it turns downstream, straight. And let's look at some videos and see if this is actually happening. Okay, so this is the airplane taking off. The vortices are not coming from the tip, but from the the end of the. This is from the tip, and actually this one comes from the tip. So you see the vortex going in and going down, right? Right in the beginning, and this is much harder to see. But like if you look at the very beginning airplane, so it's quite obvious, right? This is not just the moving down, but moving inwards. Okay, and the outward motion afterwards is really because it is hitting the ground, right? That's the ground effect. And but if it goes a little bit higher, you can see like the outward motion kind of stops, and you still see the inward motion, and then it goes back. All right. Any more questions? Okay, so this is quite interesting, and so we can also look at some computational fluid dynamics solutions. And so, for example, this is just a very simple airplane model with a straight wing, and you can visualize the vortices from the wingtip by using something we call the Q criterion. So the Q criterion is basically the difference between vorticity and shear rate, right? So basically, it's the if you look at the velocity gradient, it's a 3x3 tensor, right? There are 3 velocity components, 3 derivative directions, so it's a 3x3 matrix at every point in space, and that matrix has a symmetric component and an anti-symmetric component. And vorticity, by definition, is the anti-symmetric component. If you remember the definition of vorticity, right? For every component is the difference between 2 derivatives. It's like dvx dy minus dvy dx, right? So it's almost the one component of the matrix minus its symmetric component, right? That's the vorticity. And the symmetric component, or the average between one location of the matrix and the symmetric entry in the matrix, is called the shear. So that's we're going to look at later. That's what drives viscous stress. And basically, the Q criterion visualizes where vorticity is a lot stronger than the shear. Okay, so, and we can see like in the plane cut downstream of the airplane, we can see the z velocity. So inside of these 2 vortices, the flow field is going down, negative velocity z. Out of the 2 vortices, the velocity going up. But one thing that's particularly noticeable is if you're able to align the airplane with the downstream plane, you're going to see that the location of the vortices are a little bit inboard, right, compared to the location of the wing. And this is upward, not downward, because in computational fluid dynamics, we are usually using a different coordinate system from like what we just looked at. The coordinate system we just looked at is aligned with the free stream. But the coordinate system over here, x is aligned with the airplane itself, which means if the airplane has a finite angle of attack, the free stream is going not exactly in the x direction, but primarily in the x direction with a slightly z component, right? So this is why if you look at the far field, the z velocity it's not going to be zero. Zero would be very blue over here, right? So basically that makes it. We're going to look at computational fluid dynamics towards the second half of the course. But in CFD, it's much easier to keep the same mesh and change the free stream conditions when you want to change the angle of attack, rather than having to rotate the geometry, rotate the mesh, but use the same free stream condition, right? That's why usually the x-axis is aligned with the airplane model itself, rather than aligned with the free stream, right? But like if you're able to align with the free stream, you're going to see the center of the vortices would be not only inboard a little bit from the tip of the wing, but also a little bit lower. Okay, questions? Now, one of the consequences you can see is how the vortices move around an airplane with winglets, something like that, right? So now we have additional bound vortices, not only on the wing, but also on the winglet. Which direction does the winglet induce the flow? What? Outward, right? So there are multiple ways to understand the benefits of having winglets, right? One of the way is it generates thrust, right? Because you have tip vortices, you have a strong tip vortex coming out of the junction between the wing and the winglet, right? So the induced flow on the winglet goes inboard, right? Goes in. And if the winglet goes downward, it will be going out. But for a winglet like this, it goes in, okay? And that means in order for the lift vector to rotate upstream, right? The lift vector has to point inboard. And for the lift vector to point inboard, you need a low pressure region inboard and high pressure region outboard, right? That means the vorticity, the circulation around the wing has to be like that, right? So that vortex points. Basically, you have a if you draw the vortex, you get a strong vortex. Let's say gamma over here, and you get a weaker vortex. Let's say gamma prime over here, and gamma prime over here. And the flow induced by these vortices on the winglet would induce a flow field that's not going down but going outboard, right? That counteracts with the effect we have seen on the last slide. And as a result, if you look at how vortices move around the wings with winglet, you see we no longer observe the inward motion, right? At least the inward motion would be less than for a airplane without winglets, right? All of these are ways to analyze, for example, what is the kinetic energy distribution behind the airplane and figuring out what is the induced drag. All right, so let's continue on looking at the vortices, but now starting to look at the dynamics, right? What is not only the velocity field around these vortices, but also what is the pressure field, right, around the vortices, starting on Friday. All right, that's going to go into our incompressible potential flows. Cool. So yeah, see you.